All right, guys, so here is what we need to know about electrochemistry for the test, which is going to be on Thursday or Friday, depending on which period you're in, and also on the final. So in electrochemistry, you need to know two things. One, how to construct and diagram a battery, and the other one, how to balance difficult redox reactions. We're going to study and review both of those right now. So a galvanic cell, or an electrolytic cell, is made up of two metals in some kind of solution. So always there is two different beakers right next to each other, and then there's two electrodes that stick out of those beakers, and then a salt bridge that goes between the two, and those are filled with some kind of solutions. Now, it doesn't matter what two metals you use to connect these two things. Those come later. So let's say that we used iron and silver. So one of these is going to be iron and the other one's going to be silver, which is Ag. Now you'd be given always in the problem the standard reduction potentials for silver, which is 1 plus E minus, reacts to form Ag. And the standard reduction potential for that is 0.80 volts. And for iron, iron is 2 plus 2E minus, reacts to form Fe. And that is negative 0.44 volts. So these two numbers are going to tell you which way the electrons are going to flow, because one of these reactions is going to have to be flipped around. One of the rules about batteries is the overall standard voltage, the overall cell potential, has to be positive. So we're going to have to reverse one of these reactions. And when you reverse a reaction, you change the sign of its standard reduction potential. So the one we're going to have to reverse is going to be iron, because that'll give us a positive 0.44. If we reverse the silver, that would give us a negative 0.08. And so then when you add those two together, you get negative 1.24. So we reverse iron, and so iron's no longer like this. It is now Fe, reacts to form Fe2 plus 2E minus, and now the standard potential for that, because it's no longer reduction, it's oxidation, is 0.44 volts. So we add those two together and we get 1.24 volts, and that's going to be the standard potential of the cell, but we'll get to that in a second. So we have silver, and it's in a solution of silver nitrate. So silver is a 1 plus, which means it's going to just have one nitrate ion there, because 1 plus and 1 minus. Iron is FeNO3 2, because it's a 2 plus, so we need a 2 down there. All right. Now, which one is oxidized and which one's reduced is going to tell you where the electrons are produced. So iron is losing electrons. Iron's producing electrons, and as we know, losing electrons is oxidation. Iron's losing electrons, so it's the one being oxidized. So oxidation is going on the iron side, and it's literally on the sides of the piece of iron that's inside there. That's where the reaction's taking place. That's where the electrons are being transferred between two things. So oxidation is losing electrons. So iron's losing electrons, and those electrons are going up through the wire, traveling through the wire, and coming down the other side. And so that's what's happening over here, is it's gaining electrons. So reduction is happening on this side, specifically on the surface of the silver electrode itself. And as we know, reduction is gaining electrons, because gaining electrons is reduction. And we can remember those acronyms by saying that Leo the lion, L-E-O, losing electrons, oxidation. Leo the lion goes grrr, right? Goes grrr. So Leo goes grr, or you can use oil rig. Oxidation is losing, reduction is gaining, or whatever acronym you want to talk about. So we know oxidation, we know reduction, we know the way that the electrons are flowing. We also need to label which one's the anode, which one's the cathode. We do that by remembering the red cat. So reduction is the cathode, right? Because of the red cat, right? Remember the red cat that's on the board. It may or may not be on the board when you take the actual test, so just remember it's there. And remember the red cat. And over there, this side's the cathode, this side must be the anode. So cathode and anode. And the only other thing you would really need to know is which way the ions are going in the salt bridge. And the salt bridge is almost always made of potassium nitrate, KNO3. And that's because KNO3 is really cheap, and it's very soluble, and it's not super reactive with anything, and so very easy to make salt bridge. And you can make it out of whatever. You can make it out of ammonium nitrate or potassium chloride, I guess, but yeah. So we got, actually you wouldn't really want chlorides because it would precipitate out with silver, so that's why we use nitrates, but meh. All right, so which way is the potassium going? Which way is the nitrate going? So you have potassium ions in there and you have nitrate ions in there. Now, the easiest way that I can think of to do it is just to complete the circuit with the negative charges. So the electrons are going this way, which means that the nitrate's going to have to go across and complete the circuit. The circuit of negative things goes around. So the nitrates are going to go this way and going to go down into this solution. So nitrates are going to be coming out of here. And really it's because we're gaining more ions. As the iron is oxidizing into iron 2+, you're getting an excess of positive ions. So the nitrates have to come out of here to balance out those positive ions. So the nitrates are going this way, which means the potassiums must be going this way. Potassiums must be coming out of that side. And that's because on this side, we got silver ions turning into silver, and that's going to deplete the positive ions. So the potassiums have to then come out to replace the positive ions. So that's the direction the ions are going. The salt bridge, the way that the electrons are going, and all the stuff we need to label. The last thing I'd ask you is what is the standard reduction potential, but we've already figured that out. This thing is called the standard reduction potential, or E standard for the cell. It'll be 1.24 volts. So that means that galvanic cell, that electrolytic cell can produce 1.24 volts as it is running at standard conditions. And standard conditions mean 25 degrees Celsius and 1 atmosphere of pressure and 1 molar concentration for the dissolved salts. All right, that's all that you basically need to know for the battery part of it. The other part you need to know is how to balance a difficult redox reaction. So the redox reaction we're going to use is the one that we gave you in class that some people had a chance to finish and other people did not. So we're going to use CrOH 3 plus ClO3 minus reacts to form CrO4 2 minus plus Cl minus. So there's the redox reaction that we are going to use. So step 1 of this, and we're going to go down here so we have enough space. So step 1 is going to be to split into 2 half reactions. What I mean by split into 2 half reactions is I'm going to take the things that deal with chromium and I'm going to make them their own reaction over here. So CrOH 3 reacts to form CrO4 2 minus. Then I'm going to take the things that have to do with chlorine and make them their own half reaction over here. ClO3 minus reacts to form Cl minus. So 2 half reactions. That's the first step. Second step, we are going to balance non-hydrogen or oxygen elements. So anything that's not hydrogen or oxygen. In this case, in the half reactions, nothing is not hydrogen or oxygen. So we got, chromium is, but there's still 1 and 1. Chlorine is, but there's still 1 and 1. So we don't need to do anything for that step. If there had been something, then we need to do something, but there's not. Step 3, balance oxygens by adding water. So we're going to add water molecules to whichever side we need to get more oxygen. So be careful here. We got 3 oxygens on this side, and we have 4 on that side. So we need 1 more oxygen on this side. So we add a water molecule, H2O, to that side. We only needed 1, so we got 1 more now. So we got 1, 2, 3, 4 over here, and we got 4 over there. Here we got 3 oxygens and none on this side, so we're going to need 3 waters on that side to begin. Okay, next thing. We are going to balance hydrogen by adding H pluses to whichever side we need. And so we look at our things now and we see where the H pluses are. So here we got 1, 2, 3, 4, 5 H pluses. And so we got 5 H pluses on this side too. Here we have none on this side and 6 on this side. So we need 6 over here. So plus 6 H pluses. All right, next step, we balanced everything except for the charge. So we're going to balance the charge by adding electrons. So let's look at the charge of the 2 sides. Here, nothing is charged. There are no charges listed, so this side has a 0 charge. Here, we have -2 and +5. Well, +5 minus 2 is +3. So this side is more positive, so that's the side that needs the negative electrons. So we need to add 3 electrons on this side in order to balance out those +3. So now this side does not have +3, it has 0, just like that side. Over here, we have positive 6 and negative 1, so that is a positive 5 total. And here we just have a negative 1, so that's a negative 1 total. Now this is a little bit weird because you look at 5 and 1 and you think 4 is the difference between 5 and 1, but this is a positive 5 and a negative 1, so the difference between that is actually 6. If you look at a number line, and here you have 1, 2, 3, 4, 5, and here you have negative 1, and here's a 0, right? The difference between positive 5 and negative 1 is 1, 2, 3, 4, 5, 6. So we need to add 6 negatives to this side, and add 6 negatives to that side. So 6 electrons, that cancels out this positive 5 and makes it a negative 1. So now they're the same on both sides. They don't have to be 0. They just have to be the same on both sides. Okay, so we balanced out the charge by adding electrons. Next thing we need to do is we need to make the number of electrons the same by multiplying by a factor, if we need to. So if the number of electrons here and here are the same, then we don't need to do anything. But in this case, they're 3 and 6. They have to be the same number before we start adding these back together. So in order to make this 3 into a 6, we have to multiply this entire thing by a factor. And we need to multiply it by a factor of 2. So 2 times this entire thing. So I'm going to rewrite that with its new factor in there. So it's going to be 2H2O plus 2CrOH3 reacts to form 2CrO4 plus 10H plus 6E minus. And so now we have that one and this one with the same number of electrons. And we need that before we add them together because that's the next step. Next step is going to be add reactions together. Add those 2 reactions back together. So we're going to write the entire thing. We got 2H2O plus 2CrOH3 plus, so that came from right here. And then we're going to add the other part of the reactants from over here, plus 6E minus plus 6H plus ClO3 minus. So that was this part right here. Then we go to the products. So we first have our chromium products, 2CrO4 minus plus 10H plus 6E minus. So that was this part right here. And then we also had the products of the other reaction, plus Cl minus plus 3H2O. So that's all of our stuff from one side to the other. Now, the last step is going to be to cancel and consolidate. All right, cancel and consolidate all the stuff that you can. So now we can cancel definitely the electrons. We have to be able to cancel the electrons at this point. We can't have electrons left over in our ending equation. But we can also cancel some other stuff. We can cancel the waters on both sides. Here we have 2 waters and 3, so both of these waters cancel out, and 2 of the waters cancel out, so we just have 1 left. We have 6 hydrogens and 10, so all 6 of those cancel out, and 6 of the 10 cancel out. We're left with 4, and I think that's the only things we can cancel. Yes, the electrons and hydrogens and oxygens. We should not be able to cancel anything else other than those. So our full and final equation is going to be 2CrOH3 plus ClO3 minus reacts to form 2CrO4 minus plus 4H plus Cl minus plus H2O. And there is our full balanced reaction from this reaction up here. It is a long process, but it is the simplest one that I know. Okay, that's what we need to know for the test and the final.